it. I hate updates. I so hate these updates. It's like really now. Okay, let's go here. Have I hung up my session?
Is this your own IDE?
Pretty much. Give me a second. I'm going to terminate this. Okay, let's start with this page. I found this thing on GitHub, github.com, mschuld, RTX2000 simulator. Where the hell is my chat? Found my chat. Found this here. Why doesn't this cut and paste, damn it? Control C, so Control V, na also. Speaking of which, what's my keyboard? Oh, German, yeah, that could only go wrong. So this is where this thing is at. There are two zip files here. You can clone this thing using the usual git command logic. This thing is old. It was pulled from floppy disks in '97, and from the way it looks, it might have gotten written in '91. It's by Phil Koopman, no idea how to pronounce that. But he has a really nice page out here that discusses the architectures of these things. We have the Harris right here. Where's my chat? Jumping between these is tedious. This is Zoom, screen sharing. Damn it. Oh, that is. Come, chat. So this thing comes from here. If we look at this, minimize. So basically you have the lowdown on this thick, has an ALU, top of stack, has interrupt stack control, the usual suspects. The instruction summary, like the Novix, this thing is a directly coded CPU. So everything that you do in a command hits something in the processor. So if you read binary, you could, in theory, disassemble that in your head. And yes, that's a tall order. The Novix, if I remember correctly, is close by. I need to get this out of my way because I can't see enough. Chapter 4, blah, blah, blah. The Novix is shortly before, after this thing. Maybe this is previous section. What's this? Ah, there he is. The page before that. The page before that talks about the Novix. And if we look at this thing and compare it to the RTX, you can see that they are related, because this is extremely. Nah, come on. Is this? Yeah, here we go. If we look at this diagram, top down, and if we look at the next one, which is the previous one, this is the Novix. And if we look at the RTX, similar, but the RTX has more stuff on board. To be expected, it started out with the Novix as the grandfather and intellectual baseline, and then it got upgraded Then they added a couple of things to it. Couple of versions of it. There's a 2001, there's a 2010. Fine. Thing is, boards with that on it are impossible to find. So if one wanted to play with this, one would have to talk simulator. So there is such a thing. Let me get this back. Want to hit 8. Clickety. Here we are. My password. Anybody remember my password? Well, that wasn't it. Na also. Okay, we change the settings so that this becomes readable even for the ones with us with small screens. Where is it? We do appearance. We change. Come on. So, how's this? Does anybody have an issue reading this? Yes, no, maybe. Say something.
Absence of evidence is not evidence of absence.
Yep, that. So, cool. We'll run with it. Let's take a look at what we have. We go here, RTX2000. So when this thing explodes, one of the directories it creates is this. I shoved a little bit of documentation in here. The simulator is down here. And that's it. Comes with a makefile. Makefile is simple. Very simple. It does not use configure. This thing is so bloody simple that it can get away without. So we can just do a make and it compiles this whole thing. Done. There's a little script called run, which invokes the simulator and a hex dump of the firmware. If we do take a look at the hex dump of the firmware, well, that looks like Intel hex. I mean, there are two formats how you do hex dumps typically. One is Motorola, the other one is Intel. Well, this is your EEPROM dump, so there you are.
X is Intel. S records is Motorola.
Yeah, but it's all hexadecimal. The only difference is the framing. S records typically start with a file name and have other fluff around it. This is just straight hex. Both have checksums. Both have an end record. Both are easy to generate. So that's pretty much a no-brainer. The other thing that's nice about this piece is there's this. It not only does the simulator come with source code, and there's very little adaptation needed, it also has this here. It provides its own source, Forth source code, comes with it. So when we read through this, there are a couple of configuration constants. You can define a certain target that is an RTX DB, which seems to be one board. There's a Fox board, which appears to be or have been, past tense, some card that you can plug into a PC or something along that nature. You can compile for one of 3 CPU types. I have not touched this because I'm not sure what the simulator itself is good for. So far, I've had an interesting time to get this working. One thing that one has to be aware of once one starts running this stuff is these boards do not have contiguous memory. They appear to have ROM at the bottom and RAM up above. And at least for the RTX DB version, there's a hole, which means if you start out assuming that you have 64 kilobytes of memory in this system, and you address something somewhere, you get a diagnostic that this region is not backed by memory. I found this so annoying that once I started playing with that thing, with this simulator.
Nice. This is a huge debugging help.
Yes, it is. But what I did was take it out. I want lots of memory. I don't want holes in my memory. So I'm going to make myself a lot of memory. Unlike the Novix, by the way, this thing can address up to 1 megabyte RAM. But its program counter and its addresses are 16-bit. There are CPU registers which provide the highest 4-bit of a 20-bit address that you need to address a megabyte, that for code and data access define the missing 4 bits. So it's a little bit like an 8086. It has segments. It can do more than 64K. It has segments. This particular Forth does not make use of them. It just compiles into the very first, into segment 0, and that's it. So you can use this. You can use the segmentation. The simulator supports it, but this Forth firmware does not make any use of it. Well, it defines a couple words. You can either compile for ROM or RAM, so that you can either burn this, quote unquote, into an EPROM. Since we don't have any EPROMs, what happens on the back end of this, this code makes a memory dump. The firmware build environment creates a memory dump, which is binary, straight binary, and you take a bin to hex utility that's bundled with this to convert that into your Intel hex file. And that's it. This whole thing is fairly straightforward. Documentation of this is economical, which means you need to read source code to figure out what this thing does. And as you will find out, there is quite the need to read source code, because let's just run this, shall we? We do a /run.
This is nice, Cornelius. It almost looks like a 79 Forth.
Yes, it is. It's old. Like, the simulator was from the 90s, and the rest, I bet it is up to 10 years older. I would have to look up this app Forth. I mean, this particular version admits that it's from end of July of 1990. But still. Okay, let's see if this thing takes anything. Blödsinn. 7, 3 plus dot. Cool. Very nice. Let's see what it can do. Oops. By the way, each time you hear a tick from my keyboard, hopefully through the mic, I have to push
This is
carriage
just
return.
unbelievably slow.
No, even worse. You have to, for multi-line output, you have to enter carriage return for each individual line. And that was the first thing that I ran into.
Isn't that a matter of configuring your virtual terminal or something?
No, it is not. And let's take a look. That's actually a really good question. Let's
Is
take a
it
look.
made for calculator like these two-line displays?
Uh-huh. But let's find out why this is so. Let's take a look at the source code. So if we look for the definition of words, here is the word definition for words. So it finds out where your pointer chain is at, fine. It issues a carriage return, fine. Has a begin loop. Begin, come on. Begin repeat loop. You have begin up here. You have repeat there. Okay, fine. Let's see what this does.
Not fine.
It loads the variable turbo C and does an if against it. And if turbo C is true, then it invokes pause. And the if block ends here, then it pulls the next word and does that until done. Okay, fine. It also counts how many words it's found and says this at the end. Our little bit of a hang-up seems to be this. Huh. Okay, fine. Let's find out what turbo C is. So we go, oops, I didn't want to do that with my escape. Let's look for turbo C. Oh, there it is. It is set to 1. Huh. That's interesting. Set to 0 for simulator running on a Spark station, 1 for PC. Cool. We are done, right? Let's for the for grins. Just check what this does. Pause is invokes idle. Doesn't matter. Pauses until I hit a key. Never mind escape. Escape has moments. So what we have here is we could just set this to 0, but it's a constant. It's a constant compiled into the binary. Huh. That means if I do a load against this constant, the constant ends up on the stack. So that's it.
You could probably regenerate the X file based on the disk.
I could do that. But if we look for turbo C, note that it is not read from memory. It's not turbo C commercial alpha, like commercial C fetch, like this here. This pushes the 1 onto the stack. That means this 1 shows up in the source code n over k times. There are many occurrences of this. If this was just a memory cell that we were loading, That would be one thing, but in this case, you're pushing a 1 onto the stack. And this turbo C is referenced here a couple times. Ouch. Cool. No big deal. We can, of course, try to recompile our source code. How do we do that? For starters, this is one straight text file. So unlike the Novix and Chuck's Moorforth, this thing does not seem to do screens. So I cannot just simply do a 1 load, 2 load, 3 load, and so on and so forth. No, I have to apparently go out and feed this to the compiler somehow. Okay, how do we do that? Let's find out what we have. Maybe this thing has a load command. Oh, yeah, it has a load command. Wait, what? Count, open file. Interesting choice for a word, by the way. What does do? Let's find out. :huh. Ah! It's an abort. You flip out of something. Nice. I like it. Anyway, load. If we take a look at the definition of load, seems to using count. That looks as if we are doing a counted string and we pass it to open file. What is open file? In case you're wondering, we are going down a rabbit hole. Open file takes apparently a text and a length of text and returns a handle. So it seems to do a $20, hex 20, and pass it to command. Oh, what the heck? Let's just try this stuff. Let's see what it does. Now that we have an idea what we might feel like doing, will you do a dot run?
Looks like a system.
You typed in XC into the source, didn't you?
I didn't save it.
Okay, all right.
If we look at up forth, it does not have today's date. So yes, I changed something, but I did not save it back to disk. So if we run this, /run up forth. No, wait, we just do a run. And we found a load command, and the load command seems to take a string, app forth. Oops. That's not cool. Now we know that the load command tries to open a file. And that seems to send a $20 somewhere. Spoiler alert, it goes to the console or it goes to your terminal. And this is caught by the simulator. In that case, let's take a look at the simulator. And yes, I'm speeding through this a little bit. The files of interest here is if we operate outside resources through a serial line, just like the Chuck Moorforth for the Novix, it sends an escape character, and followed with this escape character, there is other data. So the outside world has to implement a finite state machine so that it knows at which point in a command it is at. The finite state machine for this emulator is maintained in state.c. And where is, this thing? No, wait, I'm looking at the wrong thing. No, we don't want to stay. We want to have this host.c. Okay, there's a lot of Forth in the end. Ah, yeah, here we go. So what happens is, depending on what kind of command you send into this thing, you end up either in host read, which means you have a read operation from disk, or you end up in a host write, in which case you have a write. No, sorry. Host read is invoked whenever you do a read from one of the RTX's internal registers to make interfacing with the outside world as cheap as possible in this simulated environment. A design decision was made to write to a non-existent CPU register. Like the Novix, the RTX has a couple of registers that you can do a short literal fetch against. In other words, you read or write a CPU register. You can have 31 of these, and not all of the indices are used. I think the Novix has 17. This has a few more, like one of the segment registers for extended memory access are new registers that are missing from the Novix that are new to this. But they took this one step further. One of these CPU registers writes to the outside world. Another, when written to, sends a byte out to the outside world. Reading from the same register expects something from the outside world. So it's a very, very cheap way in terms of code to talk to the outside. So our thing that went sideways was we couldn't do an open file. I suspect that this thing was trying to read. So we would have liked it would basically write a hex 2.0 into this register, and that results in an invocation of x open file. Let's find that. X open file. Oh, this doesn't look good. If never. What is never? Let's find out. Never. Not defined here. I wouldn't be surprised if it was 0. Let's find out. Grep never in star.h. Oops, grep never in star.c. Not defined. Grep never everywhere. Not defined. Therefore, this is wrong. I mean, no, let's try this again. Therefore, never is always evaluates to false, and your open file from up here to down here doesn't take place, and you get an error 1 command not supported. Ouch. There is, interestingly enough, a hint towards the existence of a finite state machine that tracks progress through something and that then evaluates certain states, and depending on these certain states does something. So an open file opens a file for read, or so it seems, that's the intention, and returns a file handle. It really does. A little bit of experimentation leads to that conclusion, and yes, it took a while. Now, if we go further, close file invokes error 1 right away. Read file, write file. This gets repetitive. But what we see here is this thing has infrastructure, or has at least stubs for an infrastructure that you can talk to a file system at a fairly high level. It can do list file. I'm not sure if that's meant to be You read the contents of the file or you read the contents of a directory. Haven't gotten there yet. Hey, you can delete files. You can create files. So this almost sounds like NFS for serial connections. But none of them is implemented. And that's a problem. Because since none of these is implemented, we cannot compile ourselves a new firmware. New firmware requires disk access. I do not have disk access, therefore there's no new firmware. And Turbo C, this constant, is baked in multiple places in the source code. This isn't funny. So the very first thing is we have to get rid of this thing. This pause is annoying. So we get out of here. We go into PL1. That's my fluffed up one.
If I were you, I'd rename that never constant to something like has file system or something.
Yeah, but then you still have to implement it. And that's what we're going to get to next, because it is not sufficient to just rename this constant or just completely rip it out. You also have to still write the code that accesses the disk. Because you have the stubs, you know what's expected. But that was what is expected is not there. So
What
if
is
we
your C compiler?
this is GCC.
And it accepts if undefined symbol input?
Seems to.
Oh man, that is plain wrong.
I know. I don't care because I'm going to rip this out. It's going to get to leave the bit. Maybe I haven't seen it yet. Maybe it's, let's see here, grep never everywhere. I don't see it. It seems to be that if this never is not defined, it evaluates to fall. Well, fine by me. I don't care because this is not going to stay for long. If we
That's
take
that's something I would do. I'd define a constant like that to stay there until I was finished with something.
But again, this is a hack. So from that perspective, let's not be too strict. And it was hacked in the 90s by somebody who admitted that he is not, that he at that time wasn't very familiar with C. So by all means. So if we want to take this further, and this is where things get interesting. I hate this keyboard. If we compare this against the previous version, we go out of here, we go to Sim 2000, and we look for host.c. On the left, we have the original, where the contents of X open file reduces to error 1. So with a little bit of time and trial and error, I implemented the finite state machine that backs X open file, because what happens is this. When you get X open file and you are in the default idle state of the finite state machine, you know that you have an open file command, you hold on to that, and you clear the space for where the file name goes. Because the next thing that you will be sent is the file name of the file that you're supposed to read open. To open a file for write, you have to invoke X create file, not X open file. X open file is read only. So if you just get the command, you initialize your file name, where you stash the file name. If this gets invoked again, the next byte that's popping out of your simulated environment is the length of the file name itself, low byte first. The next thing that comes out is the high byte of the file name length, of the high byte of the file name length. That means your file name can be up to 64 kilobytes long. And since we are talking a Unix file system here, it can include a path. It does not have to be in this directory. Now that we have a counter, following bytes are going to be the bytes of the file name itself. So we hold on to that as long as the counter isn't 0 yet. And if the counter drops to 0, then we open this file, and the app Forth inside the simulator expects the handle to the file. We get that with file number. So we have to hold on to the file pointer because we used fopen. And we do that for a reason. We do not use open for block-oriented access. We use fopen, and the reason will become apparent in a minute. So we hold on to the file number, the file descriptor, the FD, but we also stash the file pointer. We will need both later. Then each time we increase the state of the finite state machine. And once we are done, once we have the full file name, we set the FSM back to -1. And that's it. Close file, very similar, much nicer. We get the, out of this one, we get the file descriptor. If we have a file pointer to that thing, we close the file, we set this back, go back to sleep. Read file was, I didn't need that because read file appears to read the whole damn file into memory. We might not, remember, we only have 64K, so that might be a little bit of a tall order. What the simulator then does, by the way, write file, same thing as before. If the finite state machine is in a state of 0, it's initialized, we don't have anything to do. The next byte coming out of the simulator, out of the app Forth within the simulator, is the file handle. We hold on to it. Then we have the amount of data that's going to follow, and that can be up to 64 kilobytes. And we allocate a buffer for that so that we can write this stuff. Anyway, it goes on like this. When we have the number of bytes, we allocate a buffer so that we can do this in one write operation. And of course, since we are paranoid, we always allocate a couple of kilobytes extra. Bad habit, I know. Oops. But still. Anyway, once we get into a finite state machine state of 4, we collect these bytes and we reset the finite state machine 1 back so that we stay in this state. Once we have enough bytes, we write this stuff and we repeat.
Where do you free it?
Repeat that, please.
Where do you free that buffer that you are located? On close?
That gets either freed upon close or when I write the next time. So it will get freed. This thing, let me just find this. Good point. Let me find it. Ah, here we go. If I have an existing buffer, I'll free it right before the next write operation. So the, oh wait, that's read line. That's the next one. Okay, we need to talk about that too. We have just one line buffer, and this thing gets freed up gets freed up before next use. There might be a memory leak here. Anyway, where do I have malloc? Maybe you should fix that while on the call, but I just accidentally typed something. Let's not drag this in, but get this back. We look for malloc. Okay, there's one. And this is write file. So on write file, he already gets, yeah, the line buffer gets freed before I allocate the next one. And the same applies for read. Oh, yes. And here is the reason why we did not use open, but rather fopen. We opened this file as a stream. We did not open the file as a, we do not open the file for block access. Fopen is for streams, lends itself to line by line by line by line. Open is for blocks where you read a block of a given size, and if there's any formatting in there, it's up to your application level to deal with this. I do not want to deal with this. I'm lazy. And from looking at the code, it becomes obvious that this particular implementation of Forth eats source code not by screenful, a kilobyte at a time. No, this thing eats line by line. So that's the reason why open file uses fopen stream access. So what this then does is it sends in the 2f is the command read line. It sends the file handle must exist, and it wants the number of bytes to send back. What goes back is the number of bytes read from disk, 2 bytes LSB lower significant byte first, then the higher, then the payload, and a flag to indicate if there's more or not. I think that can also be used to indicate an error. I haven't had that. I haven't tried that yet. Anyway, we have our trusty finite state machine. If we are in a state of 0, we just would initialize something, nothing to do. Case 1, lower byte of maximum amount of data expected. I only do 255, so it really doesn't matter.
My paranoia.
No, wait, that's the handle. That's the handle. That's the file ID. That's the ID which file I'm reading from. Sorry. Then
my paranoia comes back to bite me again.
Okay.
When you free that line buffer, shouldn't you really set it to 0 as well explicitly?
No, because I allocated right after.
Yeah, no, but in the oh yeah, okay, oh yeah, absolutely, yeah.
So this thing, yes, the line buffer, initially it is 0. It's a static pointer up here. So this is function local but persistent. So it gets initially set to 0 at startup. So for the very first read, this free doesn't take place because line buff is 0, but then it gets mallocked.
Then it's automatic, yeah.
Yep. So the code or the app Forth sends you in 2 helpings, in 2 consecutive writes. It sends to you the number of bytes that it maximum expects. Do not send more because bad things will happen. I mean, you will crater your app Forth. You will hang yourself up. So it sends 2 bytes of length information, what it's willing to accept. Of course, we always allocate extra because I've seen others overrun my buffers. We do a shitload of debugging that wasn't there in the original simulator, but it helps if you're debugging. This kind of noise comes in incredibly handy. if you're debugging a finite state machine for which you have very, very little documentation, like none. So what we do now is we read a line from disk. Hopefully this line is not too long. Newsflash, it really worked so far. And we use fgetS. We read a line from disk. If we got a line, then we hold on to the number of characters read by string length because we need to send this back. The result is the number of bytes read lower half, and that gets sent back into the simulator. It only seems to, that gets sent back. The next state sends back the higher 8 bits of the number of bytes read. And then you send back one by one the payload of what you got. So the result variable, that's 1 byte out of this line buffer. And eventually we finish all that stuff once we have set everything. Good. There are a couple of other things in here that I haven't tried yet. For instance, you can issue commands. Unfortunately, these are DOS commands, like MS-DOS. Well, we are not running in that, so that will quite likely fail. And that's that. There are a couple of this particular implementation is what's needed to compile the thing, to get the source code to compile itself. That's one thing that I added to this thing. The other one deals, to get this working, the other one deals with this pause. And I have to find out where I did this. Ah, yeah, the other one. Remember this pause instruction that we talked about where I had to push enter, enter, enter to get one more line of output? So, remember, this thing reads its firmware upon startup. You invoke the simulator. If we take at the run shell script, you invoke this with the name of a hex dump. If we take a look at a hex dump, at this hex dump, if we decode that, let me find that. Did I put debug help into this? Anybody read my memory, please? Let's see, how did I do this? A20, blah, blah, blah. I read stuff, debug hex. Oh, lovely. I did this at compile time. You gotta be kidding me. That was dumb.
You have this under source control, of course. Huh?
Yes, here, one tar file at a time. Okay, debug hex. Where did I do that? Grep debug hex. Star.h. Ah, here we go. So, prints data. I already have that. I just need to run this thing and capture its output. Okay, cool. We can do this. /run to larger and 1 tf1. Exec format error. Why is that? Ooh, lovely. I'm running on a Raspberry Pi, and this here was compiled for Intel. That means I downloaded this whole tarball from an Intel Linux machine. It says there in the end, lib64 LD Linux-x8664. Embarrassing. Let's clean up and compile real quick. Perfect. Let's try this again. We have a hex dump. We Control-C out of this thing. We now take a look at the hex dump. Well, that font sure makes sure that we can't see. Let's look for pause. I still don't see it. Where is that? Ah, up here. See this? Here we have pause. Pause starts out somewhere over here, and it starts with a question mark. That would be this. Here we have our pause command. Let's just find nice and dandy. And what we have here in our source code is an A020 low byte first. If we take a look at, where is it? Hexin.h, hexin.c, R020. So, what I did here is basically this. To get rid of this annoying pause, I found in the hex dump the location where pause starts. Remember, Forth dictionaries. How is a Forth dictionary organized? A Forth dictionary consists of a pointer to the next word or previous word, previous in term of memory, the word before that, then the length of the name, and then the code for the word. Simple case. You can iterate the pointer chain, you compare name with name with name when you're compiling, or when execute, you execute that directly, and by jumping into the first instruction of a word. Fairly simple. So what you have is the link field that points to the next word. You have the length of the name, and you have the name. And after the name, the binary code starts. So if we find ourselves the location of where the string, the name, pause ends, the word after that is our first instruction. And we overwrite that, we replace that with hex A020. For the RTX, that's just a return from subroutine. So when we jump into pause, we come immediately out of that thing. So if we run that, we get the usual snowstorm. Let's see if we can still do something. Oops, plus punkt. That works. But now we want to do a words. And there are our words. And all of this just took place without having to recompile the source code. Because our previous version, the one that we looked earlier, the original, does not have any disk access. The stubs are there, the code is not. So, shall we maybe try to compile the source code? Nothing tests harder than production, right? I don't always test my code, but when I do, it's in production. Let's load this stuff. The load command, again, does not accept, like in Chuck Moore's Forth, accept the index, the number of a screen up front. This particular one is followed by a file name. So it asks what it's supposed to compile for. If you were to compile for, to make a ROM, to make a new hex file effectively, then you would say yes, or just hit enter. Otherwise, you end up with a copy in memory that you could jump into directly. So the default is yes. We say yay, and he compiles. This will take a little bit because we are talking a simulator, and app_forth.forth has a couple of commands baked in that at the end of compilation, when fed to the interpreter, which eats this whole thing line by line. So you have an interpreter which has support for line-by-line compilation as opposed to screen compilation. Executes a couple direct commands in between. It tells you where it went. It tells you how much code and data you had produced. All that stuff resides, that's hard-coded, starting at address A000. It saves 4,000 hex, so 16 kilobytes of image, and it will save image that writes this whole thing into app_forth.bin. If we exit out of here, we do a Control-C. Once we exit out of here, we have an app_forth.bin. This then gets converted. This is not being read by the simulator directly. The simulator wants to see hex, easily tweaked, but I thought I at this time had done enough damage to the original, so we left that for a later moment of annoyance. If we look at binhex.c, shit, I wrote this? Okay, whatever. This opens a file blockwise. It reads a block. It emits the block with proper framing. It puts a proper checksum at the end of it, creates an end bracket. That's it. And with this, you would have your own version of we would have our own modified version of Forth. With this in place, we can now easily go out and set this turbo C variable to 0 so that this is no longer in the way. And we can then also bake our own commands into this firmware. But once we do that, what else needs to change in the simulator? Once we change away from the original provided firmware, we need to remove this patch that patches the binary. Because each and every time you compile something new, depending what you change where, your memory lineup will change too. So this address where pause resides, that's hard-coded. You might step on something else in the process. So why don't we get really, really risk unaverse and convert this firmware to something normal? Let's make sure we have a copy of the original, because it would be a pity if that got stepped upon. Copy move app forth. No, wait, that's the source code. We do not want to do the source code. We want to do the hex at forth.hex.original. Then let me quickly check how to invoke. I should know this, but I forgot. Blah, 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 file name, blah, blah, blah. Okay, let's just try this. We invoke bin to hex up forth dot. That was bin, right? Up forth dot hex. File format error. Why that? Bin to hex. Or yet another one of those. My makefile needs to change. It needs to blow away when I do the clean. I did a clean. Make clean. So make. Thought I did that early. Oh, the double colon might have confused him. Bin to hex Mahlzeit. Okay, we have this stuff. File bin to hex. What the hell? Na also. So, bin to hex. Make sure, okay, appforth.bin. Bin to hex up forth.bin. So there we have that.
You're
And
a
I need to,
you're a secure bastard. You don't have dot in your path. That's very
of course
nice.
not. I might
That
be,
is
I
cool.
mean,
I
I
don't
might be
either.
naive, but I'm
I
not
don't
that
either.
des. So now we have an upforth.hex that looks reasonable. Wait a second. I forgot to set turbo C to 0. This wouldn't even work this way. Great. Just great. Perfect. Okay, upforth.forth. We want to set turbo C to 0. Only change in this thing. First one. Next one, hex in.c. We need to strip. This here needs to go. Because just in case, this now is supposed to work cleanly without any binary patching. So let's not do that. We run a make again so that we get a new simulator without this binary patching stuff in it. We run that thing. We are still up. 3, 4 plus dot still works. Load up 4.4. Na also. Yes, I want to compile for ROM. We wait for a small eternity. This is a Pi 2. This is all single threaded, so you get 900 megahertz performance for something that used to be way, way faster back when. Ooh, the name has changed. It's now sunforth.bin. Fine. Let's get out of here.
Yeah, I saw that in the code. It switches on that turbo C.
Yep. Yes,
Yeah.
it does. Yes, it does. So now we do a, what else? /bin to hex. And we want to do this for sunforth.uppercase bin. And we want that in sunforth.hex. Clickety. What else? We do take a look at run. Okay, fine. We just run manually sim2000 sunforth.hex. Let's see, test case. Enter words. And there are my words without any binary patching. So that means this thing does compile itself. And setting this dumb constant to 0 gets me a decent looking binary that is now hopefully completely DOS free, free of DOS legacy artifacts. Sure, and that's pretty much how far I got with this thing. Again, documentation is, at least in this tarball, kind of non-existent. So you have to read the source code, first one. Second one, for the purists among us, so me too, it doesn't support screens. So that is probably something that I would retrofit fairly soon, simply because I'm lazy. And I like my old-fashioned environments. And the last thing is the missing stubs for disk access, because they're interesting. Now, depending on platform, you could decide if you want to continue doing that over the serial port and then to a host system, if you had a real system running this, or if you would just like to stay with a local file system, if you were to run this on an ESP or anything else that has an SD card slot. So you could run this on a microcontroller, because the requirements against the outside are fairly slim. The basic simulator in its original form just does console access, and that's it. There are no file stubs. The file stubs are for you to implement. So if you were to use the Arduino environment to do this on an ESP or Teensy or what, and you have a memory card, you could link in all the code that talks to an SDHC and the files, the FAT file system that you typically find on an, on an SDHC. Oh, and there's another important difference between this one and the Novix simulator. For that, I need another, do I have that? No, I do not. I need another screen so that we can quickly switch. Give me a second. I'll be right back.
Right here, or?
Yeah, what's up? Yes, I have. Shall do. Okay. Bye. Good. So one important difference between the Novix simulator, my version, not Ulrich's, between Ulrich's does this probably nicer. Mine really bit bangs a serial port like the original does. One nice thing about the simulator, if we run this, Sim 2000 Sun Forth.hex. There we are. If we do a words, we see something. This thing is up and running. If we do a top, we find out that one thing that does not show up at the top of the list is the simulator. The simulator is idle.
But systemd does.
Yeah, systemd is a piece of shit that should have never been turned into the wild.
Would you please define a word and run a C against it?
Yeah, that would be nice. Give me a second. I'm after something else. Give me a second. Sim 2000. If we look at this thing, it has not accumulated any CPU time. If we look on the other hand, I have to find out if I have this thing on here, 4016. Oh boy. Let's find out which one of these is latest. That would be February 9, February 16, February 19. tar xfz, this thing. So we do this again. Now we have a 4016 directory. If we file nc 4K, LD Linux, oh, good grief, make clean, make. This takes a little bit. The Novix simulator is a little bit more, it's not quite as snappy.
You can do a make minus J4 or something.
Yeah, could, but wouldn't make much of a difference, only 4 CPUs. If we run this thing and do a go, he will wake up. See how this, the output came way slower, the copyright message. If I do a words on this one, see how this is walking across? Unlike the RTX, that comes courtesy of this particular simulator, really bit banging I/O pins that are, he's really bit banging physical I/O pins, and that's being simulated too. So instead of writing into a CPU register to a pseudo CPU register to talk to the outside, this one bit bangs a port at quote 96 kilobit unquote. That this has consequences. If I run a top against that one, look who is up here eating 100% CPU. Right up here, our Novix simulator is just busying out one CPU. So if you have any processor in a laptop or something where you have an issue with your power or temperature budget, you might not want to do that. So one of the things that I'm quite looking forward to would be to take the I/O capabilities provided by the RTX simulator and backfit those into this one so that I can get rid of the bit banging, which would be a somewhat legitimate thing to do, because quite frankly, there are not that many Novixes around. And if somebody wanted to simulate that thing, then that somebody should not be forced to spend way too much extra time in way too much time into waiting and burning CPU times for nothing. Good. Of course, they both run concurrently. I just have to find the screen where I put them. This is the Novix from the looks of it. This is not it. And here we have the RTX. So if we do a words over here, this is fast, because he does not bit bang. He writes a whole byte to read, to send into CPU register. That's it. He will read a whole byte from a CPU register and wait for it if it's not already there. So if we were to do a, oof, does Raspbian have a P stack? Which P stack? Doesn't. Bummer. We could have looked, we could of course attach a GDB, but oh well. Anyway, what was the question a moment ago?
The
Oh,
user C on a user-defined word.
On a user-defined word. Yes, let's get out of here and stop the Novix simulator so it doesn't eat so much CPU. Let's see here. Colon, blah, 3, 4 plus dot semicolon, C blah. Oh, there is your, yeah, look, there is your code. You have an address. It starts at hex 8000 because that's, oh, yeah, about that. The problem here is, remember, this thing simulates a board that used to exist. This board has RAM towards ROM at the low end, RAM in the higher 32K. So your word definitions end up, well, up there. So in this case, we start out with the code at address 8008. Before that, you still have the link field. You have the length of, oh, excuse me for just a second. So, are you all still there?
I wish
back.
I could do the same thing.
So,
I
yeah,
have to go cut the grass now. So I'm leaving, but this code is super efficient. It's
yes,
very...
it is. It is very nice, very efficient code. Oh yeah, that's another change that I stuck into my version of the simulator. It does no longer segment. There's no memory hole. In other words, you start out at address 0 with RAM, and you end at 64K at this time with ROM. Upping that to 1 megabyte, which this thing can easily support, is not a problem. Just change a malloc because the memory access code understands segmentation. So that makes for shorter code because the distinction between memory-backed and memory not backed code goes away. Everything is backed. And you can read and write everywhere. That is very similar to the Novix because the Novix at startup copies its firmware from ROM chips that get selected upon read into RAM, which gets selected upon write. Then it flips a bit somewhere that causes the gate array logic chip that's somewhere in there to now only select RAM and forget about the ROM. So this has just become, with that in change, this is way more similar than to what the Novix does. Performance-wise, these things make for compact code. They are really good at that. So that stuff, well, it just does. So, yeah, long story short, there you have it. That's all there is to it. So yes, it's quite efficient and it's snappy. The implementation is, like with the Novix, fairly easy to read, but it takes a while to dig through. The nice thing is you know exactly what your code words do because they go straight against parts of the CPU. So once you have ingested this diagram, and which one is that? 5.4. This is, yeah, this is the Harris. If you look at this, your instruction set is right here. Like the Novix, by the way, code jumping to an address seems to work only if the address, wait a second, how did we get up there? How did we get up here? This code resides up there. How did we jump there? I need to do some digging. Anyway, exit is not quite named correctly. That should be a return from subroutine. Anyway, here we have, oh yeah, subroutine call. Subroutine call, highest bit is 1. No, wait, this is instruction set summary. The description of the opcode is underneath, not above. So this is not a heading because this down there no longer looks like a subroutine call. Anyway, well, that is that. Again, if you've seen the Novix, the RTX is very familiar. You can do a couple of extra things to it, like address more memory. But beyond that, once you have gotten used to this version of Forth that it is running, or you manage to port something of your choice, this will immediately feel like home. This is fairly easy. It's fairly easy to code. One thing this thing does not have just yet is the ability to single step through code. But since the code runs in an execution loop that is extremely similar to the Novix simulator ones, baking in single-step support and then being able to look at what the registers do is fairly straightforward. Just takes time to write it. Cool. This concludes pretty much the show and tell. Again, the code is on GitHub. This is still in the works, but once it is something that I'm not totally embarrassed of showing off, it's probably going to show up on at one of the usual watering holes for your viewing pleasure. Cool. And now for the important part of the day. Are there any questions? Are you still awake?
So when's the FPGA version coming out?
Whenever I learn how to FPGA, I have no idea how to do this. What there will be, though, because that is lower hanging fruit and easier for me to attain, it's less of a learning curve. The simulator, as far as its I/O capabilities go, is not very demanding. It's a lot of low-hanging fruit there. So you could, for instance, get that working on a Teensy or another sufficiently fast enough micro controller, as long as it has enough memory and preferably a little bit of oomph too. You could get this working on a comparatively small CPU and at least hook up something on the outside directly. It would not, of course, not be as fast, but it would give you the same look and feel as the real thing without having to go through and build a whole new system with this.